For decades, computing followed a linear path. A human provided a specific input, and the machine executed a rigid, deterministic sequence of logic to produce a final output. Even large language models follow this passive pattern. They wait for a prompt, compute a probability distribution to generate a response, and then immediately terminate. In an agentic loop, we wire the model's response back into the system. Generated text becomes a functional trigger for external actions, forming the perceive, reason, act loop. Using its outputs to drive subsequent inputs, the system progresses towards its goal without human intervention. The engineering challenge has moved from simply scaling model parameters to architecting these continuous, autonomous orchestrations. Agency is defined by the threshold of orchestration. While an assistant handles narrow tasks under human supervision, an agent manages the complexity of multi-step execution on its own. Early autonomous systems, like the reinforcement learning models that mastered games like Go, learned through millions of trial and error cycles. These systems required massive training phases to discover optimal strategies within the strict mathematical boundaries of a game board. Modern LLM agents use natural language reasoning to achieve zero-shot generalization. They can navigate novel problems and diverse software environments without the need for brute force retraining. An AI agent is fundamentally a compound software architecture that utilizes an LLM as its central reasoning engine. To understand how these systems scale, we need to deconstruct the architecture by building an agent from the ground up. We start with the LLM at the blueprint center. It's stateless. Once an execution completes, the model clears its workspace, retaining no memory. To maintain continuity, we introduce the memory module, providing the persistent state required for multi-step tasks. Short-term memory tracks the immediate conversational context and the active variables of the current assignment. Long-term or episodic memory uses vector databases to store historical data and the successful outcomes of past actions. Before evaluating a new goal, the LLM retrieves this context, allowing it to ground its reasoning in its own history and past environment states. This transformation allows the LLM to function as an entity capable of tracking a changing environment over time. Even with memory, the reasoning engine is still isolated. It can generate text about a database, but it cannot inherently write to one or trigger an API call. To interact with the world, we add tool connectors, allowing the model to communicate with external software. When given an objective, the agent uses its reasoning capabilities to autonomously select the correct tool to execute the task. The LLM structures the necessary API parameters, such as formatting a precise SQL query, to bridge the gap between digital reasoning and a tangible state change in the software. This dynamic tool calling is the mechanism that allows an agent to execute work in the real world. Giving an LLM memory and tools without a planning framework is an engineering risk. Without governance, the system may fall into infinite loops of redundant or expensive tool calls. Engineers use the react paradigm to govern interactions through a reasoning and acting cycle. The agent outputs a thought, takes an action, and observes the result, refining its next thought and repeating the cycle until the goal is achieved. The risk of react is latency. Processing the context window after every observation consumes massive tokens. A more efficient alternative is rewu. It requires the LLM to generate a complete dependency graph of all tool calls before executing any external action. Decoupling the reasoning from the execution phase avoids the redundant model calls of a React loop and drastically lowers the token cost. Selecting the correct planning topology is the primary factor in managing the computational overhead and response time of an agentic system. Not every task requires a complex LLM planner. Deploying a heavy reasoning loop for a basic automation is a waste of compute resources. The autonomy hierarchy determines the most efficient architecture. Tier 1, simple reflex agents use hard-coded rules. Tier 2, model-based agents add memory. Tier 3, goal-based agents plan specific sequences. Tier 4, utility-based agents optimize paths. Tier 5, learning agents autonomously improve logic using feedback. Engineering mastery is the ability to match task complexity to the correct tier. Over-engineering leads to excessive costs, while under-engineering ensures systemic failure. At enterprise scale, a single agent is rarely sufficient. Complex workflows require a network of multiple specialized agents collaborating in a decentralized environment. These systems typically run on serverless cloud infrastructure to manage the high compute demand of multiple reasoning loops firing in parallel. This enables specialized routing. A lightweight classifier agent can filter simple requests, escalating complex queries to a high-capacity reasoning agent. However, this scale creates systemic risks. If a single upstream agent hallucinates, that error cascades, corrupting the downstream workflow. Multi-agent systems significantly expand enterprise capabilities, but they also multiply the risk of uncontained systemic failures. Running these systems in production requires strict governance to manage the complexity of autonomous interactions. Absolute traceability is mandatory. This involves continuous activity logging and unique agent identifiers to track every autonomous decision. High-stakes actions are managed through human-in-the-loop constraints, ensuring that an agent cannot execute a critical financial or security change without explicit human approval. This shift changes the fundamental responsibilities of the software architect. Modern software engineering involves designing the resilient environments, robust tools, and strict guardrails that define the boundaries of an autonomous reasoning engine's behavior.